Alright, good morning, good afternoon, good evening class. This is Mr. ARocena, and on today's video we're going to be talking about indicators. Indicators are weak acids or weak bases, and they're usually organic in nature. And one of the things that makes indicators really interesting is the fact that they adopt different colors depending on whether there's more of the conjugate base form or whether there's more of the conjugate acid form. So a generic example would be something like this. You have an indicator that is yellow in its acid form. Here's my pen. So here we go. So this is acid form. So this is in its acid form because it has the extra H there. And then in its base form is red. So base form. Notice that it's missing an H. Okay. So in its acid form, it is one color. In this case, it is yellow. And in its base form, it is another color. In this case, it is red. So an indicator basically is just a substance that has different colors depending on whether it's an acid form or whether it's a base form. And it's really interesting because it actually helps us identify whether a solution is acidic or basic. Or is, well, not necessarily acidic or basic. Basically, indicators help us identify whether a solution is more acidic or less acidic. And this is because when you look at that equilibrium again, you can sort of see that if the indicator is placed in an acid solution, there's an excess amount of H3O+, so it shifts the equilibrium towards the acid form. So acidic solutions will contain large amounts of this, and it forces the equilibrium to go backwards. And because the equilibrium is shifting backwards, that means that the indicator is going to adopt its acid form more readily. Alright? And what this means is that there's going to be more yellow color, less red color, so the substance becomes more yellow. And as a general rule of thumb, an indicator will adopt its acid version when it is placed in acidic solutions. So it kind of makes sense. If the solution is acidic, then it forces the indicator to adopt a more acidic form. Now the same can be said for if you place the indicator in a basic solution. So in a basic solution, you have a lot more, or a lot less hydronium. You have a lot less hydronium. So the equilibrium will shift in such a fashion as you make more. So this amount here is very small. So you have very small amounts of hydronium in a basic solution. So the equilibrium shifts this way. As a result, you get less of this or of this. So the solution ends up taking a more red color because you have more red indicator. And much like in the previous slide where we mentioned that the indicator is in its acid form in acidic solutions, in basic solutions, the indicator will adopt a base form. Now, if you end up being somewhere in between, then you end up getting a mix of colors. So if you recall back to the titration lesson, titrations always go towards an equivalence point. And at the equivalence point, this is where we reach an equal amount of hydroxide to hydronium. So if you put an indicator at the equivalence point, then that is the point where the color just begins to change. So if we had a yellow indicator and a red indicator, the equivalence point would adopt an orange color because you would have equal amounts of this and equal amounts of this. So you end up getting an equal mix of both of those. So neither form of the indicator is favored, meaning that you get a mixture of yellow, red, and that ends up being orange. That's all an indicator is. It's just a substance that has a different color in its acid form, different color in its base form. And we use indicators to help us determine kind of what's the pH of a solution. Based on how the indicator changes color, we can calculate them. Now, every indicator, being a weak acid or a weak base, has a Ka or a Kb. We tend to just stick with a Ka for indicators, so we assume that the indicator is a weak acid of some variety. Now it turns out that the Ka of an indicator is equivalent to the concentration of hydronium that causes the color change. And it kind of makes sense a little bit, because if I go back to our equilibrium here, the Ka is really just this is based on this equilibrium. So if the Ka is based on this equilibrium and nothing is shifted, then we'll have equal amounts of this, and that'll be the Ka. So the Ka of an indicator indicates kind of how much hydronium is needed to change the color of the indicator. And by extension of knowing this quantity here, you can calculate the pH using the pH formula, negative log of the concentration of H3O plus, and that'll allow us to calculate the pH of the color change. So if we know that if something causes the indicator to change color, then we know what that pH is of the solution after the color has been changed. Now there's one thing of note, and this applies to titrations and indicators. In a titration, the endpoint is when the color changes, and in a titration, we stop when there's an equivalence. Now for acid bases, this equivalence point occurs when your OH minus is equivalent to your H3O plus. What we would like to do is when we reach the endpoint is ideally the same as the equivalence point. We want to choose an indicator that'll change color approximately around where the equivalence point occurs. Now, during the actual process of titration, we stop titrating when the color changes. Now, depending on how we choose the indicator, that color change might occur somewhere that's not at the equivalence point. So we always want to choose an indicator so that the endpoint is the same or approximately the same as the equivalence point. All right. So, for example, we'll ask what color is the indicator in the following solutions. Now, before we get started on this example, we have to take a look at another table in our data booklet. So in our chem data booklet, this table appears right after the table of Kas, and this is the table of acid and base indicators. So you can see here that we have a bunch of indicators and we have their pH ranges where they change color. And in this column here, it tells us what the color changes go. So for example, methyl violet, pH range of 0 to 1.6. This is the range where it changes color, and it'll change color from yellow to blue. So if your pH is 0 or less, methyl violet will show as yellow. If your pH is 1.6 or higher, methyl violet will show as blue. And if the pH is somewhere in between, it'll be some kind of mixture of yellow and blue, depending on whether it's closer to 0 or closer to 1.6. Another popular one we use, especially in earlier science classes, is this, phenolphthalein. Phenolphthalein has a pH range of 8.2 to 10, so that's where it changes color, and it goes from colorless to pink. So colorless, phenolphthalein will appear colorless at pHs of 8.2 or lower, and then as it gets to 10 and higher, it becomes phenolphthalein is interesting because, like I said, this is the more common indicator we use in a lot of reactions. But a lot of reactions we do in earlier science classes always end up being a strong acid and a strong base. And the equivalence point for those reactions is always should be around pH 7. So the fact we use phenolphthalein as an indicator for those reactions is actually kind of not. We should be using something that changes around pH 7. Ideally, that would be something like bromthiamyl blue, phenol red, even. All right, so in this question, we're asked what color is methyl orange in a solution that has a concentration of 1.5 times 10 to the negative 13 molar KOH. So in order to find the color of methyl orange, we need to know what pH this solution is going. However, we don't actually know, we don't actually have the information to calculate pH directly because we are given a strong base. So what we can do instead is calculate the POH. Being a strong base, we can use the leveling effect to show the following. So strong bases, they will create an equivalent concentration of hydroxide. And we'll just carry out this calculation. So this gives us a pH of 12, or so POH of 12.8. Which then we can use the fact that pH is just 14 minus POH, and this will give us a pH of 1.2. Right. Going to our table, pH of 1.2 1.2, and this is methyl orange, so there's methyl orange. pH of 1.2 is less than 3.2, so it should show as red. Since the pH is 1.2, methyl orange, orange. Alright, this example is similar. Here we'll have bromthiamyl blue in a solution of 4.5 times 10 to the negative 6 molar HNO3. And what color will this be? Again, we'll need to know the pH. Here we have a strong acid, so we can just use the leveling effect to show the following. Strong acid will create this much hydronium, and we carry out that calculation again. So this gives us a pH of 5.3. Check our table. Here we have a pH of 5.3. It's less than 6, so bromthiamyl blue will show as yellow. So bromthiamyl blue is yellow. Now, when a question asks you to calculate the Ka of an indicator, the process is similar. Because we know that the Ka is the concentration of hydronium at the color change point, we'll have to we'll have to calculate where that color change is going to be. So it says here then that phenol red changes color over the range of 6.6 to 8.0. Reminder that less than 6.6 it's yellow, greater than 8 it's red. So we want to calculate the pH and the Ka at the end point. So the end point will be where you have equal amounts of yellow and red. And this is very intuitive. It's exactly at the halfway point. So at the halfway point between 6.6 and 8.0 is at that point you'll have equal amounts of yellow and red indicator, so it'll end up being you have equal amounts of the hydronium and hydroxide and hydronium. So this pH is going to be let's see, halfway between 6.6 and 8.0 is 7.3, sorry, 6.6. So you take the two ends of the range and then divide by 2. That's how we get our pH of 7.3. Alright, and then the Ka concentration of hydronium is just 10 to the negative pH. So this will be 10 to the negative 7.3, which is approximately 0.0005. So basically 5.0 times 10 to the negative. Then you can do the same calculation for all the other indicators. So the pH at the halfway, you can just basically take the low pH, add that to the high end of the pH, and then just divide by 2. And at that point you can use Ka is basically the concentration of hydronium at the halfway point, which would then be 10 to the negative pH at the halfway point. Now, knowing that indicators change colors at different pH ranges, we can actually combine indicators to make what's known as a universal indicator. So when we make a universal indicator, this is really just a mixture of 2 or more different indicators. Usually we use a mixture of 3. So let's suppose that we're going to use the following 3 indicators to make ourselves a universal indicator. And what colors will be made at each pH. Now, as we make this universal indicator and decide what colors are made at each pH, you should hopefully see that there's going to be some issue with the indicators we've chosen. All right, to work out this problem, we need to first identify what pH range each of these indicators change color at. So methyl orange goes 3.2 to 4.4. All red goes 6.6 to 8.0. Saline is 2 to 10. Okay, so there's our pH ranges. And we'll set up a table. Table will look like this. We have our indicators here: methyl orange, phenol red, phenol phthalene. Our first, this will be our pH. So we have pH is less than 3.2. That's the lowest range we have. And we have pH of 3.2 to 4.4. pH range of 4.4 to 6.6. Basically, I'm just writing out the different pH ranges that kind of overlap. We have our 6.6 to 8.0 pH. We have our 8.0 to 8.2 pH. Last range would be 8.2 to 10, and then greater than 10. I think that's what I want. Yeah, greater. Sorry, not like that. Alright, so now we just write down what colors each indicator are at each pH range. Oh, and then I guess resulting color. I guess resulting color goes here. Result. Alright, so less than 3.2, methyl orange is going to be red. Phenol red is going to be yellow. And this is clear. So the resulting color for pH less than 3.2 will be a mix of red and yellow and clear, so that will be orange. 3.2 to 4.4, this will be orange, because that's methyl orange changes in that pH range. Phenol red is still going to be yellow. This will be clear. So orange and yellow, this will be a, I guess a lighter orange. 4.4 to 6.6, methyl orange will be yellow. Phenol red will be orange in this area. Phenol phthalene will still be clear. So here we still get a light orange color. 6.6 to 8.0, this will be yellow. I could actually fill this in for all of this because we know that's all going to be yellow. Phenol red will be red, and this will still be. So this is again, this one's going to be orange here. And 8.0 to 8.2, this will be clear, so this will still be orange. Here, this will be sort of a light pink color. Here, it'll be a darker pink color. Daily. So our combination will be sort of like orange and pink, and this would be also a darker orange. Alright, so these three indicators would then have those following colors. If the pH is less than 3.2, you'll have an orange color. If it's between 3.2 and 4.4, it'll be a sort of light orange color, and that light orange color continues to about pH 6.6. 6.6 to 8.0, you have an orange color that actually extends to about 8.2. And then you have this orange pink color for anything past 8.2. Alright, so there we go. So this universal indicator will give you effectively 1, 2, 3, 4 different color ranges. But there's a problem because color range, or the pH here and the pH here have the same color. So this universal indicator is actually not that great because orange appears at 2 different pH values. If I use this universal indicator and I get a orange color, I don't know whether it's at pH 3.2 or whether it's somewhere between 6.6 and 8.2, which is, they're both quite different. One is highly acidic, one is kind of close to neutral. So the choice of indicator, we have to change one of the indicators. most likely we'll have to change this one or this one to a different indicator. Culprit is basically I want to make sure that the color change either at this pH level is different than the color change at this pH level. Now one of the easiest ways to do that is you quite simply, rather than using phenol red, I would actually probably opt to use bromthiamyl blue. Bromthiamyl blue has a color change of yellow to blue as opposed to yellow to red. You could also probably use bromcrysol green to blue change there as well, and let's give you a different color. So there's our quick sort of lesson on what indicators are and how to deal with some of the calculations. We talked about the issue of selection of indicators. You can replace one. So replace, my solution would be to replace phenol red with bromthiamyl blue. There's a second one that you could easily do as well. There's a good replacement for methyl orange that you could replace as well. So you don't have to use the bromthiamyl blue that I suggested. Your assignment then for this video is as follows. And if you guys have any questions, you guys know how to contact me.